Good afternoon, everyone. I'm Sudarshan Majumdar. I'll be talking on behalf of Professor Sankaran Aniruddhan from Indian Institute of Technology, Madras. And his paper is on the area and power efficient receiver for narrowband Internet of Things applications. So during the course of my presentation, I'll be going through the following outline. I'll first start by introducing the 3GPP standards for NB-IoT receiver, and then lay the specifications on which the authors have designed the circuit. Then we shall move on to the NB-IoT receiver circuit design in details. And then I shall talk about the measurement setup and the measured results. And finally, I will conclude my talk. So narrowband IoT communication is a standard which provides low power, wide area connectivity between devices and systems. So the proposed bandwidth specified by this 3GPP for this NB-IoT is around 200 kilohertz, and specifically in India, band 3, which is around 1805 to 1880 megahertz, and band 5, which is around 869 to 894 megahertz, are reserved for NB-IoT. So this slide shows the scope of this work. Here you can see within the demarcated red line are the different circuit blocks which make up the NB-IoT receiver. So the authors have presented a system level analysis as per the 3GPP standards, and they have shown that it satisfies the functionality of the receiver. And they have also shown circuit level optimizations to minimize power control. So this slide shows the derivation of the noise figure, which is done as follows. From the 3GPP standards, we can see the specifications. The signal has a bandwidth of 200 kilohertz, and the signal itself uses QPSK modulation. And the required SNR for the signal is around -1 dB, and the overall sensitivity is around -108.2 dBm. This allows us to directly calculate the desired noise figure, which was calculated to be around 13.8 dB. And obviously, from the OSCHIF components and process voltage temperature variations, we'll always get some loss. And taking this loss into account, the desired receiver noise figure was calculated to be around 6 dB. Now I shall talk about the gain range and nonlinear derivation. From the 3GPP standards, the input power from the antenna can vary anywhere between 108.2 to -25 dBm. So this specifies the maximum input RF power to be around -25 dBm. And the receiver output power level is assumed to be 0 dBm. And the peak to average power ratio of the QPSK signal is about 5 dB. And the desired RF front-end minimum gain is specified around 25 dB and maximum gain around 108.2 dB. And the desired input P1 dB is around -20 dBm. So let us now talk about the circuit design. So here, the scope of the work shows that the circuit consists of a low noise amplifier, a mixer, which is a quadrature downconversion mixer, a frequency divider which is a divide by 2 counter, which generates 0 degree and 90 degree signals for the mixer. And also additional buffers in the mixer allo path will be shown. And the authors have also achieved a 3-bit gain control, both for the LNA and the mixer. This brings us to the low noise amplifier, which is actually a 2-stage low noise amplifier because we want a large gain. And also because the entire setup has to be concentrated on a very small area, on a small die area, we want no inductors. Therefore, the authors have devised the geometry or devised the topology towards having a topology with no inductors. This naturally brings us to the stage 1, which is a capacitively cross-coupled common gate LNA. The input matching has been set by the input bias resistance and the GM of the input transistors. And because cross-coupled capacitors were used, this allowed the authors to reduce the noise and also increase the gain twice. And the overall gain which has been achieved for this NB-IoT for this stage 1 is around 20 dB. The second stage is a simple self-biased inverter with a gain of around 12 dB. And the overall gain for the low noise amplifier is around 32 dB, and which and also they have achieved a very competitive noise figure of around 2.7 dB. So the active mixer is a simple Gilbert cell-based active mixer. The input transconductance stage is nothing but two differential NMOS transistors, stacked on top of which is the allo switching stage. And the output load capacitance creates a pole at 400 kilohertz, and it relaxes the filtering requirements for the next stage. And bit B3 is used to switch between two loads, the active and the passive loads. This allows us dual mode operation. The passive load is used for high linearity while it has low gain, and the active load is used for low linearity for high gain. And a negative feedback loop sets the gate voltage of the transistors. And because of this configuration, a compensation is needed, and the compensation capacitor CC provides the Miller compensation for the loop. Now, the input allo path is defined by a pair of D flip-flops, which creates phase differences of 90 degrees. So there are four phases: 0, 90, 180, and 270. And this has been achieved using a pair of D flip-flops. And the input to the inverter has a capacitance which is very high, and therefore we need buffering stages, which has been achieved using three numbers of inverters. Now, the process variation simulation has been shown in this slide. The noise figure of the receiver in the highest gain configuration degrades from 6 dB to 9 dB with process variation and temperature variation. And this is actually within the specifications laid by the 3GPP. The lowest gain configuration also has an input P1 dB specification, which is greater than -20 dBm in both bands for all process variations, which also satisfies the 3GPP linearity requirements. Now let us look at the measurement setups and results. And this slide shows the chip level micrograph and die level micrograph. And this entire chip has been fabricated in a 65 nanometer CMOS TSMC process and packaged a QFN48 package. The input and LO receivers here have been provided at opposite ends so that there is less coupling between the two, and the axis of a kind of axis of symmetry is maintained to reduce the IQ mismatch. So the measurement setup looks like this. The input has been given by an analog signal generator and a wideband balun, and it shows the PCB on which the chip is mounted, and the measurements are done in a high definition oscilloscope. Now let us talk about the gain and input matching. Ideally, we'd want that the entire power which has been received by the antenna is delivered to the mixer, and it requires that the S11 against the gain control sequence is less than -8 dB, which has been duly achieved in the first frequency. And also the gain control also follows very closely what has been achieved in simulation as well. So this is the overall performance comparison of this NB-IoT receiver. As you can see in this table, that the specifications achieved by this NB-IoT receiver has a very comparative value compared to the recently reported work, which are based on the 65 nanometer process. And also an important thing to note about this NB-IoT receiver is that it operates with a very low supply voltage, which is around 1.2 volts when compared to other 65 nanometer technology implementations. So I will finally conclude this talk. In this work, an inductor-based wideband low-power receiver has been presented that can be easily integrated into end-to-end NB-IoT remote sensors. The direct conversion receiver comprises the LNA, IQ down conversion mixer, and the LO divider, while also implementing a single-pole baseband filter response. The prototype IC has been designed and fabricated in a TSMC 65 nanometer CMOS process, and the Measurement results validate the analysis design performance of the front end system. And also, as I have reiterated in the previous slides, the receiver also satisfies the gain, linearity, and noise specifications as per the 3GPP standards. These are the references used in this work. Thank you.